So, we're going to talk about alcohols. So more than just the alcohols from the coop. Like you might be thinking, like, I know alcohols. Like there's Grey Goose, there's Jack Daniels, there's Jameson. I got all the alcohols. I'm good. I got to take it a step further than that. All right. So alcohols, as you know from Organic One, right? They have this OH group. One of the big kind of like things that alcohols let us do is alcohols allow for hydrogen bonding. Right, so if you remember, I keep saying that, hoping that you will remember, that if you have an alcohol, right, the oxygen is slightly negatively charged and the hydrogen is slightly positively charged. And what will happen is that the positively charged hydrogen on another alcohol will interact with the negatively charged oxygen of your alcohol and make a weak bond. This is a hydrogen bond. And this will kind of happen all the way around. Right. And while hydrogen bonds in and of themselves are weak, one single hydrogen bond is pretty weak. When you have a solution of an alcohol, right, you have millions and billions of hydrogen bonds, they end up being pretty strong. Right? And the big thing that we notice from as a result of hydrogen bonding is the boiling point of alcohols is higher than you think based on the molecular weight. So ethanol has a boiling point of somewhere around 80 degrees, give or take. I don't have that memorized. For some reason, I know the exact density of triethylamine, 7.27 grams per ml. I learned it like 20 years ago, and it's just in there now. I don't know why. Like, if I'm stuck on a deserted island, that's not going to get me off, but it's there now. Um, but if you were to get rid of that OH and just keep the same molecular weight, so if you made this an ether, right, it weighs the same. This, I think, is around negative 80 degrees C is its boiling point. So just having that OH, having that hydrogen bond donor or acceptor vastly changes the boiling point as what it would be if it didn't have that hydrogen bond. Another thing about alcohols is they are weak acids. So you can think about like that you can lose your proton from your alcohol. Now the equilibrium, since it's a weak acid, really favors just being the OH, but you can lose that proton, right? But you can pull that proton off. So the pKa of an alcohol is around 16. So that's right around the pKa of water. So your average alcohol is about as acidic as water. So you don't think of water as being like super acidic or anything, but that's where the pKa lies. But if you think about other things that we've used or we've taken protons off of, right? If you remember, right, we did reactions with alkynes where we removed the alkyne proton. An alkyne has a pKa of 30. So an alcohol is 10 to the 14th times more acidic than an alkyne. So it's not acidic in like, absolute terms of like how we think of like acids, right? But it is acidic compared to a lot of other organic compounds. Right? So if you want to remove the proton from an alcohol, so you have to use a strong base to make this happen. So the strong base that we can use is like sodium hydride. Right? So we use sodium hydride. Remember we did Williamson ether synthesis? Where you take an alcohol, you treat it with base, you make the O minus, and then you add an alkyl halide to make an ether. Right? So you can need a strong base to do a deprotonation, because strong bases and weak acids, they will react, right? Or a strong acid and a weak base will react. But two weak things don't react. So if you have an alcohol, which is a weak acid, and you mix it with the aforementioned triethylamine, which is a weak base, nothing happens, right? The amine is not basic enough to pull the proton off of the alcohol. So going forward, we're going to see reactions that have triethylamine in them with the alcohol, and something has to happen to the alcohol first to make it more acidic before the amine can take the proton off the oxygen. We have to make the oxygen make that hydrogen more acidic before the amine can do anything. So, kind of want to show again, like that alcohols matter outside of just like doing reactions with them. So, if Seroquel, there you go, Seroquel. These like sales numbers are a little out of date. I think they're from like 2015, but it was one of the top 150 drugs sold in the U.S. that year. So $300 billion. And this is an antidepressant. And if you don't know anything about the molecule, you can pick out when a molecule is an antidepressant because they all have the same structure. Every antidepressant, pretty much, or every molecule that has this aromatic ring, seven-membered ring with two heteroatoms, oftentimes two nitrogens, but two heteroatoms, and then another benzene ring, those are almost always antidepressants or otherwise neuroactive compounds because we found a good structure that gets into the brain and we just keep dressing it up in different ways because this kind of core aromatic ring, seven-membered ring, aromatic ring goes into the brain. When my wife was in med school, she was like going through drug names and then like what they did for like an exam, and she was like something benzodiazepine. I was like, oh, it's an antidepressant, and she was like, no, it's not. I was like, yeah, it is. So she like went and looked it up. She's like, how did you know? I was like, because benzodiazepines, which is when this is two nitrogens, I said they're all antidepressants. She was like, huh. I was like, so if you one day in the future in your med school, you can be like, I remember that structure. Wakefield taught me something that helped me in med school. But it has this alcohol out here. So my guess, looking at this, is this group right here, this ether and this alcohol, help with solubility. So flat aromatic compounds are, the technical term is brick dust. They just don't dissolve in water, right? So if you have a flat aromatic compound, so you've got aromatic ring, this ring's flat aromatic ring, you've got this big greasy thing that's probably a solid. that just isn't going to dissolve in water. So what they do to dissolve things a lot of times is they put pegtails on them, which PEG is short for polyethylene glycol. So OH, CH2, CH2, OH. And they will just stick these tails on the molecule until the molecule will dissolve in solution. So they have this little tail, just this little like PEG group out here to help make the molecule a little bit more stable so you can actually take it in a pill form. Right. This is Crestor because who needs diet and exercise when you can just take a pill? So like, I want my cholesterol to be lower, but I also want to eat these chili cheese fries. All right. So Crestor, you have these two alcohols here, and they're chiral. So first of all, if they made those alcohols chiral, there is no other combination of those alcohols that actually works, right? So if you make them both wedge, doesn't work. If you make the other diastereomers where one is wedge and one is dash, doesn't work. If they didn't have to have this chirality, they wouldn't, right? Because it's really expensive to have to make a single enantiomer. It's way easier to make a racemic compound to just make a mixture. So you definitely need these two alcohols to be in this have this stereochemistry. And when you start putting multiple stereocenters on a like straight chain, the molecules start to develop like a little bit of a twist to kind of like compensate and like make the lowest energy Newman projections and stuff like that. And so the shape imparted by having these two chiral centers is probably important for making the molecule work as well. Now, finally, the most important OH here, right? The OH that stands between us and meth, right here on Sudafed. So, as you may know, with enough matches and a big enough bathtub, you can turn Sudafed into a whole lot of meth. This alcohol is relatively easy to remove, and that's why in many states, if you go to buy Sudafed, they card you, and they actually track how much Sudafed you've bought in a given time period to make sure you're not going to like 17 different Walmarts and just buying all the Sudafed. When I lived in Delaware, I went to go buy Sudafed, and they carded me, and it was like, my head hurts. I have sinus pressure and pain. They're like, are you sure your head doesn't hurt because you need meth? I'm like, I'm 100% sure I don't need meth. Just give me Sudafed, please. Right. Now, I have here old Sudafed. It's kind of back to being current Sudafed. So I went through a phase where this was Sudafed. Everyone was making meth with it. So we were like, well, that's bad. We don't like people making meth. So we had a phase where we put a chlorine on this carbon. That chlorine is really hard to remove. Can't remove it in your kitchen or your bathtub. So you couldn't turn that Sudafed into meth. The problem is that for a lot of people, when there was a chlorine here, Sudafed stopped being Sudafed. It was just a little red pill that did nothing, right? Because it didn't bind properly, it didn't work anymore. So they had to go back to this being Sudafed and then like locking it up and hiding it from people. I keep talking about a bathtub. There's also the shake and bake method where you can throw Sudafed and various car chemicals into a bottle and shake it for a while, and then meth falls out of solution. I found out about this when I was in Delaware because I did like roadside cleanup with the chem club, and they'd be like, watch out for pop bottles because sometimes they're just full of like explosive like car chemicals. I was like, oh, super. Along the lines of car chemicals, have you ever like said something out loud and been like, oh, I shouldn't have said that. That's not good. Like, so I had a Homer Simpson moment when I was in grad school. I was at a Walmart. I needed to buy fuel injection cleaner for my car, and they carded me for fuel injection cleaner. And I was like, why are you carding me? And then I realized why they're carding me. And instead of just saying it in my head like a normal person, I went, oh yeah, because you use fuel injection cleaner to make meth.
Uh-oh. Did I say that or just think it?
And I was like, oh man, I wasn't supposed to say that. Am I gonna make it out of the store? That's gonna like take me down. I was like, thanks. Yeah, I was like, oh man, don't. I'm not supposed to say that out loud. A large part of fuel injection cleaner is this diethyl ether, and it's a solvent you do organic reactions in. Don't make meth. I'm not condoning making meth. Don't make meth. There we go. My disclaimer. Okay, now we're gonna go bigger. More alcohols, more stuff. This is vancomycin. You may have heard the phrase antibiotic of last resort. This, for a long time, was if we gave you everything else and the infection you had did not go away, we gave you vancomycin. So vancomycin has some alcohols around here, right? It's just basically a bunch of peptides stuck together. So this molecule is huge, right? You think like there's a lot of leeway, you could make some changes and it wouldn't matter. If you remove either one of these chlorines, the molecule does stone nothing. I don't know why, but it just does nothing. Right? So how does vancomycin work? And this ties into hydrogen bonding. So I'm going to go into biology and put my biology hat on here. Someone got a D in bio too. Let's go. So when a cell divides, right? When a bacteria divides, it's got to close its cell membrane up again, right? Or all the insides become outside, right? So there is a very specific amino acid sequence at the end of the peptides that end up getting cross-linked to close the cell membrane. And that sequence is a lysine, dealanine, dealanine, right? And so that's in green here. Vancomycin here in blue, it hydrogen bonds to this amino acid sequence. So it makes it so when the enzyme comes around to interact with lysine, dealanine, dealanine to close the cell membrane up, it can't get to it. So the bacteria can't close itself up. So then the bacteria. So this was our last chance for antibiotics for a while, right? This is our last line of defense, and eventually bacteria mutated to make it so vancomycin doesn't work as well. And what they did is, so you see these black dotted lines here, these are hydrogen bonds. So the way that vancomycin grabs onto this amino acid chain is it makes some hydrogen bonds uh, around the molecule. And the bacteria changed right here. This is a nitrogen, where this from this blue oxygen here up to this bond here, that's a nitrogen. That's an NH. NH are hydrogen bond donors, right? So you make a hydrogen bond. Well, if you change this from alanine to lactic acid, you change that oxygen to a nitrogen. Sorry, you change that nitrogen to an oxygen. Now, instead of having a group that is a hydrogen bond donor, you have a group that's a hydrogen bond acceptor. So you break this hydrogen bond. And also you have a little bit of electrostatic interaction where this here is an oxygen that has a lone pair. This becomes an oxygen that has a lone pair. They kind of bang into each other. Losing this hydrogen bond and that electrostatic interaction makes the vancomycin does nothing. So we went from having an antibiotic that we could give people when nothing else worked to now another antibiotic that sometimes just doesn't work anymore. So this oxygen right here is, I'm going to go back to slide, is this oxygen right here. And there is a researcher at Scripps, his name's Dale Boger, and this is basically what he's devoted like the last 35 years of his life to, is making analogs of this compound. They found that if you remove this oxygen and you make it an NH, right? An NH, right, has a lone pair, right? The nitrogen has a lone pair, so it can be a hydrogen bond acceptor, just like this oxygen. So in the wild type bacteria that don't have a mutation, it still picks up the hydrogen bond that you need for vancomycin to work. But it's an NH, so it can also be a hydrogen bond donor. So when the bacteria mutates and puts an oxygen there, Well, now we've just flipped it, so now that NH can donate a hydrogen and make a hydrogen bond and get that hydrogen bond back that we need to make vancomycin work. And so if you make that change, that version of vancomycin works against the mutant strain and the wild type strain. The problem is, as you can imagine, it's probably pretty difficult to change one oxygen out of a bajillion, right? So it's one of the things that like we can do it and it works, but it's now taking that and getting it to like scale, right? Because a lot of times like things like that are this complicated, right? It might be that we grow up the bacteria that makes this to like kill other bacteria, and then we just take the vancomycin out, and then we're good. We don't have to actually make this. But like making the analogs, it's difficult. It's doable, but it's difficult to like tell the bacteria, hey, can you make this with an oxygen, please? Can you just, right? You can change things and like you can genetically engineer bacteria or other organisms to make different molecules. People have done that for a while, but this is a hard like nut to crack. So like we know we have this thing, but it's getting it like to be something that we can take. So big pharma went through this big phase in like the 40s, 50s, 60s. They made a whole bunch of antibiotics, and they were like, "Yo, problem solved. Don't have to do that anymore." And well, the bacteria over time have now mutated, and a lot of our antibiotics are trash. Right? And the problem is if you're big pharma, you would much rather like devote your time and energy to things that are more profitable than antibiotics, right? If you make Crestor and people have to take Crestor from the time they're 40 to the time they're 80, right? Every day, 2 pills every day, you get a whole lot of money. If you make an antibiotic that's really good and people take it for 10 days, maybe twice a year, right? I don't know how many times I take antibiotics, maybe once every 2 years, right? You don't make a ton of money off of that. So there's not like a big drive to develop new antibiotics from a financial point of view. There is a big drive so that, we don't go back to, oh, hey, I fell down and scraped my knee. It's been a good run. I guess I'm dead now, right? Right. So like all that stands between us and like, well, I had surgery and well, now I guess I'm gonna die because I got an infection is like, a hydrogen bond here and there. So, the modern world is great, but we're like 3 hydrogen bonds from just being like, well, I fell down. I guess I'm dead, right? So I've hopefully proven to you that alcohols are important, right, and useful. So let's go over all the ways you know how to make alcohols. All right, so this is kind of like an organic one review. So there's hydroboration / oxidation. Here, you add like BH3, then hydrogen peroxide, water, and hydroxide. And this will put an alcohol on the least substituted carbon of your double bond. Right, so this is the special one because every other thing that we do puts the alcohol on the most substituted carbon. So hydroboration puts the alcohol on the least substituted carbon. Then we have oxymercuration. All right. Here you add mercury acetate, water, usually in THF. And then you add sodium borohydride and hydroxide, and that will make your alcohol. And then there's the kind of simplest way to do this, which is just acid hydration. Where you just take your alcohol, or so your alkyne, you add water and sulfuric acid, and again, you make the most substituted alcohol. So why do I have two different methods that can make the most substituted alcohol? That's because one of them goes through carbocations and can lead to rearrangements, and one doesn't. So, right, if we take the acid hydration conditions, we don't put the alcohol where the double bond is, it rearranges, it goes somewhere else, right? So we make our carbocation, that rearranges, and then we add water to that, right? But if we really want that secondary alcohol, right, if we really want our alcohol to be, on this carbon, that's when we would use like oxymercuration, because oxymercuration doesn't go through a carbocation. To make this arrow way longer than I think it needs to be. So you have your mercury acetate, your water, your THF, here you don't have to worry about any rearrangements, so you just make the most substituted alcohol. So these are all the ways that you learn in Organic 1 to make an alcohol. So I want to introduce a few new ways now, and then we'll kind of touch on them again later. But, all right. And all of them kind of come back to adding a nucleophile to the C double bond O. It depends on what nucleophile you're adding as to what product you get, but they all kind of come back to adding a nucleophile. So the first thing we have is reduction. Your nucleophile is H minus. So our nucleophile for this that we're adding to our C double bond O is H minus. So if you have a ketone and you add sodium borohydride, and then H plus, you add a hydrogen to your carbon that was double bonded to the oxygen, and you make an alcohol. When you use a ketone, you always make a secondary alcohol. So when you do a reduction of a ketone, you're always going to make a secondary alcohol. If you use an aldehyde, you're going to make a primary alcohol. Where you already have one hydrogen on the carbon. This carbon is this one here, and then I add another hydrogen to it. So this is the exact reaction that we did in the lab. Right, we took the aldehyde, we added sodium borohydride, we made a primary alcohol. Like 99.99% of your reactions or ketone and aldehyde reductions you're going to do are going to be with like sodium borohydride. Right, sodium borohydride. Right, sodium borohydride is a safe source of H minus. Right, it's not super reactive. Like you guys used it, it was like open on the bench, no big deal. Right. There are some kind of more souped up hydride sources that I'm going to introduce here that are all going to do the same thing as sodium borohydride, but it just does them with varying levels of danger. All right, so we have lithium aluminum hydride. And again, this is just a source of H minus, so you're going to reduce your ketone to a secondary alcohol. I'll do the same thing to an aldehyde. So unlike sodium borohydride, this stuff kind of catches on fire in air. So in lab, we had you take your reaction flask, we put it in an ice bath, and we slowly added HCl to it. And it bubbled and got a little hot, but the ice bath was there to kind of like keep everything under control. When I was in grad school, a guy ran a big reaction with lithium aluminum hydride, and he poured it into a set funnel and was slowly adding water to it to quench any excess lithium aluminum hydride. He was adding it slowly, the water, and the water ended up sitting on top of the solvent. It didn't go into the organic layer, and it sat there until he got a big enough like bubble of water that it just went and mixed all at once and like blew up his set funnel. Sodium borohydride, hey undergrads, play with this, you're fine. Lithium aluminum hydride, then I got like fire blanket, put out an undergrad, like stop, drop, and roll. Like that's too much stress for me. Right. Does the same thing, but with more oomph. Right. The other reagent that we can use for these reactions is Dibol. And you'll see Dibol written a few different ways. I almost always write it like capital D, then all lowercase letters. You'll also see it like Dibal. Or Dibol H. It's for diisobutyl aluminum hydride. So I always write it like this, but you might see it written other ways. Does the same thing. It's the source of H minus. And we'll add that to your C double bond O. So these all do the same thing as sodium borohydride to ketone and aldehydes, but I'm introducing them here so they're rattling around in your head so that when we get to carboxylic acids and esters, these all do different things. They react with some react with acids and not esters, or react with some functional groups and not others. So I just wanted to introduce them here, and we'll circle back to them and like kind of differentiate them later. Diol is kind of in the middle of the danger scale. It doesn't really blow up, but does everything you need to do. The very first time I used Diol, I took it out of the bottle, and there's a little on the tip of the syringe, and it went poof, and like made a little purple flame. I was like, ah! I was scared, but also I thought it was super cool. I was like, oh, it made a little flame. So I was like, it doesn't do that. I spent the next 6 years trying to recreate the purple flame. Never did it. Not one time. I was like, well, probably for the best. It's probably the most dangerous thing I'm doing. Like, can I make fire today? No. But it's not nearly as dangerous as lithium aluminum hydride. So we have reduction where we're adding H minus, and the other thing we have is addition of organometallic reagents. Here your nucleophile is some carbon group, right? So an organometallic is any compound with a carbon metal bond. So if you look at most of these things, right, have our carbon group and our metal, you would draw a little line, say that the metal is positively charged and the R group is negatively charged. So these are strong nucleophiles and strong bases. Right, and we've used organometallic reagents before in class. So when we were doing the benzene reactions with the triflate and the silicon, right, we would make the benzene and then we would add an organometallic reagent to add a carbon bond. In organic 1, we did stuff where we would take a terminal alkyne and we'd add N-butyllithium. That's just right, an organometallic, right, 4 carbons with a lithium on the end, and that acted as a base. And it will remove the proton from the end of the alkyne and make an acetylide, a lithium acetylide. And then we'd use that organometallic and have it do an SN2 reaction and make a new carbon-carbon bond. So here we used it as a base, and then this was a nucleophile later on. Right, so we were able, we already kind of seen these before. So in a general sense, when you have a carbonyl, you can have your R metal, then H plus, and you make an alcohol. When you add an organometallic, ketones become tertiary alcohols, and aldehydes become secondary alcohols. Yep. Try again. So add hydrides, you get one set of products from your ketones and aldehydes. When you add organometallics, you get another. So we kind of have three types of organometallics that you guys need to kind of keep straight. We have a lithium. This is an organolithium. A sodium. This is an organosodium. And when you have a magnesium, it's a Grignard. Because some French guy, like in the early 1900s, somewhere like 1900 to like 1910, made these, and they got named after him. So you're like, oh, cool, I just named it after the metal. No, not always. You'll notice that, one second, I'm going to die. You'll notice that um, the lithium and the sodium don't have anything else on the metal. They just have the carbon group, right? They're in the first column of the periodic table. They can only be +1. Magnesium's in the second column, and it is +2. So it needs to have two things to kind of balance it out. So the magnesium here is +2. The carbon is -1, and then the halide attached to the magnesium is also -1. Right, so that's why you need to have two things on the magnesiums, because the magnesium is just one extra positive. So we can use these. Right, you're going to bond your carbon that's double bonded to your oxygen to the carbon that's bonded to the metal. So you're going to turn that C double bond O into an OH. And then you're going to make your bond. Right, bond to the carbon that's double bonded to the oxygen, and then you're always going to make the carbon that's bonded to your metal is always going to end up bonded to that C double bond O carbon. So you're going to make your alcohol. You're going to bond your carbon to that. So always the carbon bonded to the metal is your nucleophile. Right, red carbon, blue carbon. Oops, added a carbon. So that's good. So we will go over on Monday how we make the different organometallic reagents, and then we'll get into some reactions with alcohols.